All righty, lads and ladies, welcome back. Today is student teaching day again for Natasha and Radha. They have, over the last day or so, sent me their videos. Today they're going to be going through section 3.1, which is on derivatives of power functions, polynomials, and also derivatives of exponential functions. I've had the chance to meet with them a couple times in office hours to talk about how they're going to run their lectures. They've both decided to pre-record a handful of videos, which they sent to me, so I will be sharing those videos here with you guys. If you have a question, just shout out and I'll pause the video and we can talk about something for a minute. Make sure you take notes the same you would if we were doing the lecture live on the dot cam. And then I don't think I saved one of the video sets in order, like I didn't rename them. So let me take a look here and see which one is which. Yeah, Radha's videos I don't have saved in orders. Natasha's I do have ordered. So Radha, let's take a look here. Is this still? Okay. Oh, new Kovac HEVC codecs. No, not now. Jeez. Is this a different format than the others? It is. So that's the first. Alrighty. So what I'm going to do here is I'm going to go ahead and share my screen. I think 2028, 2029, 2043, and 2044 are probably the correct order. The 1156 video is in a format that I can't open on my work computer without downloading software, which I don't have permission to. So if we have to insert some extra stuff, we will. But here we go. Let's see, is the share on? You guys, can you guys everybody can see that okay with it maximized, the video full screen? Yes, okay, excellent. Alrighty then, yep.
I cannot hear anything.
Okay, let's see what we can do for the sound. No sound at all on your end, huh? Okay. Let's try. That's so weird. So it must be some other sort of issue here. Let me see. Maybe if we run them straight from Drive, you'll get better sound. Oh, no, we have the same problem, aren't we? Let's just straight attachments. They are. All right, just so I'm clear, you guys aren't able to hear anything at all? Yeah, I can play with the microphone settings here. Let me.
Still no sound.
The share screen settings may include something about sharing the direct sound from the video.
Maybe on the share screen thing, like when you select what to share, if you select that specific like app, like the movies or whatever is playing the video, maybe it'll work.
Going over the derivatives of exponential and polynomial.
Yes, have
functions.
some
So
right
we have
now.
The power function f of x equals x to the n, where n is any positive integer, and we're just showing a couple of examples to look at the power rule. So they start off with when n equals 1. Obviously the limit of this function is going to be 1. So 1 equals 1. And then when it's 2, I'm not going to go over that right now, but it equals 2x. And then
We can't hear.
I cannot hear you.
when it's 3, we get f of x equals x to the third. And then to find the limit, you get as h goes to 0, x plus h to the third minus x to the third over h. And then you can expand this out. You get the limit as h goes to 0. You get x to the third plus 3x squared h plus 3x h squared plus h cubed, and then minus x cubed over h. These cancel out, and then you can also factor out an h here, and then these all cancel out. This becomes h squared. So you end up with limit as h goes to 0 equals 3x squared plus 3xh plus h squared. And then you can cancel these out because the h's are going to go to 0, and you end up with 3x squared. So here you get 3 equals, let me just erase this, 3x squared. And then for 4, you're going to do the same thing. I don't know if I should show it because it's like really long, but it ends up being 4x cubed, and you can kind of see a pattern here, and that's what the power rule comes in. It's so the derivative of any number x to the n is going to equal n x to the n minus 1. So you can see that here. So for example, if we were doing 5, so x to the 5th, it would be 5x to the 5 minus 4, which equals 5 minus 1, so 5x to the 4th. and so on like that. So this is known as the power rule. Okay, so we're also going to look at the power rule in terms of negative numbers and fractions. So the first example I have is finding the derivative of 1 over x equals negative 1 over x squared, and we can rewrite that as the derivative of x to the negative 1, because that's just like a rule. And then this can turn into negative 1 times x to the negative 2 power, and you can see that the power rule still holds the same for this example, so it works for negative numbers. And then we also have for fractions, this is another example. Sorry. Equals 1 over 2 root x, and we can rewrite this as, this can be rewritten as x to the 1/2, and then this can be rewritten as 1/2 times x to the negative 1/2, and you can see it still holds the same for that, because 1/2 minus 1 is negative 1/2. So you can see the power rule also works for both negative numbers and fractions. Yeah. This can be rewritten as x to the 1/2, and then this can be rewritten as 1/2 times x to the negative 1/2, and you can see it still holds the same for that, because 1/2 minus 1 is negative 1/2. So you can see the power rule also works for both negative numbers and fractions. Yeah. Okay, so we're gonna do an example now. Yeah. So we have f of x equals 1 over x squared, and this can be rewritten as x to the negative 2. So then we get f prime of x equals x to the -2. And using the power rule, we can bring this out. So -2 to the times x to the -3rd, because you're going to be subtracting 1. And this can be rewritten as -2 over x to the 3rd. And that is going to be our answer. Another example I have here is y equals the cube root of x squared. So, yeah, we're going to be finding the derivative. Of the cube root of x squared. So this can be rewritten as x to the 2/3. And again, using the power rule, we're going to pull this down. So it's going to be 2/3 x to the -1/3. And that's going to be our answer. Yeah. And again, using the power rule, we're going to pull this down. So it's going to be 2/3 x to the -1/3. And that's going to be our answer. Yeah. So we're going to be doing the last example for the power rule, and we're going to be finding the equation of the tangent line and the normal line. So the normal line is perpendicular to the tangent line. To the curve y equals x root x at the point 1, 1. So what we're going to do is we're going to start by finding the derivative of x root x. Or this can be rewritten as x times x to the 1/2, which can be rewritten as x to the 3/2. So then we're going to be finding f prime of x, because we're going to pull this down, of 3/2 x to the 1/2, which can be rewritten as 3/2 root x. So this is going to be the slope of the tangent line, 3/2. So for the equation, we're going to use the point 1, 1. So it's going to be y minus 1 equals 3/2 x minus 1. And then the normal line is going to, so this is the tangent line. And then the normal line is just perpendicular to the tangent line.
All right, let me see if I can pull us out here for just a second, make sure everything is nice and clear before we move on. First, can you guys hear me okay?
We can hear you.
Okay, good, good. So for this last example, the calculations there are being done correctly, but the notation can be a little bit confusing. So we want to find, share something, okay. We're trying to find the equation of the tangent line to y equals x root x at the point 1, 1. So you could call this thing f of x if you want. All right, that's our function. The slope of the tangent line, so we need two things, right? We need a point and we need a slope. Once you have a point on the line and the slope of the line, you can write down the equation of the line. The point is 1, 1. The tangent line has to pass through the point of tangency. The slope would be f primed of 1. And we're going to figure that out. In order to find f primed of 1, we need to find f primed of x in general. So f primed of x would be d dx of f of x, which is d dx of x root x, which is d dx of x to the 3/2. So all I've done so far is recognize what the derivative is and then say, okay, x root x, I can write that as a power function. That's x to the 1 times x to the 1/2, which is x to the 3/2. Now I'm actually going to take the derivative. So I bring the 3/2 down, and then I have x to the 3/2 minus 1. That's my power rule, right? N times x to the n minus 1. So that's 3/2 times x to the 3/2 minus 1 is 1/2. So what we've got here is that f primed of x is 3/2 x to the 1/2. So f primed of 1 is 3/2 times 1 to the 1/2, which is just 3/2. So that's my slope. And now using the point slope form of a line, y minus y1 equals m times x minus x1. We get y minus 1 equals 3/2 times x minus 1. This is our tangent line.
Here I have the other questions. Can I use the linear function? Y is equal to mx plus b, so that I just put the point 1 in the y and the x, so that again 1 is equal to 3/2 plus b, so I get the b is equal to 1/2.
You can, and that works, but it's nice to get used to this point slope form. So this, it just goes faster. You don't have to solve for b. And generally, this is considered just a more useful way of writing down an equation of a line. Mx plus b, the slope intercept form, y equals mx plus b, it works, it does. But it involves that extra step where you have to solve for b. So I encourage you to try to get used to this version, the point slope version. But yes, what you said there would absolutely work.
Thanks.
Sure, of course. All right, and let me make a quick look at the chat, make sure everything's feeling okay. All right, yeah, have we cleared up everything from the chat? Are there any additional questions we want to look at before we move on to the normal line? So I'll draw a quick picture here because we haven't talked about normal lines in class. We know what the tangent line to a curve looks like, right? I have here some point on the graph. Then the tangent line looks something like this. Insert your favorite joke about tan lines here. The normal line is the line going through that same point, but perpendicular. The concept of a normal is going to be very important in physics and in Calc 3, where you need to say what direction a surface is like pointing out at. But in our setting here, in the Calc 1 setting, the normal really isn't super useful. But you can imagine in some situation, right? Like if you're walking around on the earth and you want to know what direction is gravity pulling, it's always pulling in along the normal line towards the center. So if you have some surface, the normal always kind of points straight out. And in a lot of physics problems, you use the normal vector as something to integrate against or multiply against. It's a very useful concept. So in order to prepare you for the concept of a normal vector in Calc 3, we talk about normal lines here. The normal line encodes all the same information as the tangent line, right? If you know the normal line, then you can get the tangent line. If you know the tangent line, then you can get the normal line. So they're really equivalent notions, but the tangent line is a little bit more immediately useful to us. The last thing here I'll say is that, remember, if two lines are perpendicular, then their slopes are opposite reciprocals. So the slope of the normal line, we can get right away from the slope of the tangent line. All right, I'm going to go back here.
So it's going to be the opposite and reciprocal slope. So this is going to be, it's just going to be y minus 1 equals -2/3 x minus 1.
Very good.
And that's the answer.
All righty. So these are some really good examples of us using the power rule. I think that first video is probably the proof that didn't want to run on my computer. Let me see if I can run it. We tried this, didn't we? But it didn't work. It just gave me the option to save and show. All right. So when I look at these on my laptop, I do have the HEIC codec there. We can try to install it. Actually, I've already got it saved. See what happens if I tell it to install the codec. You serious? Pay for it. Pay for it. You're out of your goddamn mind. All right. So I think probably what I will do, because this work computer doesn't have the necessary video codec to play that file. I know it's outrageous. I will just run through a quick proof of the power rule here for you guys. Yeah, so the slope of the normal. So we saw that the slope of the tangent line, which is f primed of 1, is 3/2. And then the normal is perpendicular to the tangent. So the slope of the normal line would be the opposite reciprocal of the slope of the tangent line. So remember, if two lines are perpendicular, if they meet at 90 degrees, then their slopes are opposite reciprocal. So you flip it over, that's the reciprocal, and you negate, that's the opposite.
Okay, so we're going to be doing lesson 3.1 today, and it's going over the derivatives of exponential in a couple of examples. 1.
Yeah, no, this is the same. All right, I don't know why that chose to play again. So let's take a quick look at a proof of the power rule. So the power rule says this. If f of x is equal to x to the n, then f primed of x is n x to the n minus 1. Or in the Leibniz notation, we would say that d dx of x to the n is n x to the n minus 1. So this is what we want to prove. And the thing that we're going to need here is some version of the binomial theorem. So let f of x be x to the n. By definition, f primed of x is the limit as h goes to 0, f of x plus h minus f of x all over h, which is the limit as h goes to 0 of x plus h to the n minus x to the n all over h. And then this x plus h to the n term is the tricky one. So to handle this properly, say x plus h to the n is another thing from pre-calculus that is not normally given the love it deserves, is the sum from k equals 0 to n of the binomial coefficient n choose k times x to the n minus k, h to the k. The thing you need to know about this is just the first few terms. So this is x to the n plus n x to the n minus 1 times h plus n times n minus 1 over 2 x to the n minus 2 h squared plus other terms. And all the stuff that's in here have higher powers of h. So the capital Greek letter you see on the first line here is, this is a sigma, and it stands for the sum of. This thing right here is called a binomial coefficient.
I have a question. The binomial coefficients, the binomial functions equations is very important in the calculus one.
It does have, yeah, it's not without importance. Its main use is in a field of mathematics called combinatorics, where you count things. So this is often read as n choose k, because when you crunch this out, it's the number of ways to pick k objects from a set of n objects. For example, there are 9 students in this class. If I wanted to know how many ways could I pair you up into groups of 2, the answer would be 9 choose 2. If I want to know how many ways could I pair you up into groups of 3, the answer would be 9 choose 3. And the exclamation marks over here, these are called factorials. Factorial is just the product of all the non-negative integers less than or equal to that number. So like 4 factorial is 4 times 3 times 2 times 1. 3 factorial is just 3 times 2 times 1. 2 factorial is 2 times 1. You get the picture, right? 5 factorial is 5 times 4 times 3 times 2 times 1. All of the blue here can basically be ignored for our purposes, but if you want to enrich yourself, this is the way to do it. It turns out that n choose 0, the very first binomial coefficient that you would get here in this sum, is just 1. N choose 1 is just n. N choose 2, this is the binomial coefficient from the third term of the sum, is n times n minus 1 over 2. And in general, they look like this, which is kind of complicated. So here's what I would say. I would say the first term here is x to the n. When you multiply all this out, x plus h all to the n, first term is going to be x to the n. The next term is n x to the n minus 1 times h. And then you have terms with h squared, h cubed, and so on. Then you've got your minus x to the n. And all of that is over h. The x to the n's, just like you saw in Rada's example with the x cubes, they go away. And then the next term here, he has the piece that we're hunting for, right? The n x to the n minus 1. If you factor an h out, then you'll have that guy, n x to the n minus 1 plus everything in this parentheses here had an h squared, an h cubed, h to the 4, or larger. So what's left when you factor out an h is terms with h squared, and higher. All over h. So pay careful attention to what I've done here. I'm saying all of these terms have h squared or larger. So when you factor out this h, what's left are terms with h or larger, right? The powers of h have gone down. You can zoom in a little bit. All right. So what we're doing is we're trying to hide the binomial theorem here. X plus h to the n needs to be expanded using the binomial theorem, which is this thing, but it's a little scary looking. So what we're going to do is just pull out the terms we need. I know that when you kind of FOIL all this out, the very first term is going to be x to the n. The next term is going to be n x to the n minus 1 times h. And then after that, you have a bunch of terms with h squared, h cubed, and larger powers of h. And then the minus x to the n there is the minus x to the n here, and he eats up the x to the n there. So all that's left is this stuff. And from this stuff, I can factor out an h. This term has an h right here. And everything in these parentheses, all the stuff that I'm hiding from the binomial theorem, has like h squared or h cubed, some larger power of h. So from these pieces which survive, I can factor out an h. This term just gives up its h, that comes, right? It's out here, there's nothing, no longer h there. All of the terms in the parentheses here had larger powers of h. So certainly they can all give one up. And what's more important is that the stuff that's left over has h's in it as well. Now when I cancel, we're left with lim h to 0 n x to the n minus 1 plus a bunch of terms that have h or h squared or higher powers of h in them. Finitely many terms, but a bunch of them. And each term in here, because it has an h or an h squared, these are going to go to 0 as h goes to 0. So we get out what we're hoping to get out. We get out what matches with all the examples that we did. N x to the n minus 1, and that's the proof. It's not 100% rigorous because I'm not being very careful with the binomial theorem, and I invite you to study the binomial theorem. Right? If it's not something you're familiar with, take the time to get familiar with it, especially if you like counting problems, probabilities, that sort of thing. Binomial theorem's huge there, also huge in lots of other places. But yeah, this is about as easy as a proof of this theorem can get. Any proof of this theorem is going to require some working with this expression or something equivalent to that, which is always going to boil down to the binomial theorem. But basically, just imagine foiling this out, however big it is, realize that the first term will always cancel with this guy, that the second term always has just one h in it, and that all the other terms have larger powers of h, so that when you divide out by h, this is the only one that doesn't go to 0. So this is what we get. All right, rough sketch of the proof. You're not responsible for the proof, right? This class is, as much as we'd like to think of rigorous math class, it's more about computation. But I do want you to understand where it's coming from. So please take the time to go back through this. Just the binomial theorem. Yeah, so if you pop your pre-calc book and look in the index, you'll definitely see a section there on the binomial theorem. Another good place to take a look at that look here. Summation notation. And the binomial theorem just on the Wikipedia page. So binomial theorem is just a shortcut for expanding things like this. And it's always given in terms of the binomial coefficient. There's many proofs. I'm a big fan of the combinatorial proof because I like combinatorics. But yeah, these would be good places to start here. And then if you're curious about the summation notation itself, the capital sigma on its own, the wiki page there is quite good. Indeed. Yes, with that we can calculate x plus a to the n for any x, a, and positive integer n. There are other polynomials, right? There are polynomials that are not expanded binomials, but you can calculate any binomial expansion that way. All right. The other part of today's student teaching comes to us by way of Natasha and is about differentiating exponential functions. I'm going to go ahead and play these now.
Oh, Mr.
This part, we're gonna be.
Oh, sorry, go ahead. Yeah.
Yeah, there were actually like 2 sections I did, and I sent in the other one. Like I had
Let me see. Did I
I think like talking about like derivatives kind of in like the constant rule and stuff. I had that part. I sent it. Did it?
Oh, okay. Here we go. The
Yeah.
videos part 2. All right. I have not saved or reviewed these yet.
Yeah,
So
you can do. I mean, either section's fine. Yeah, and I had them out of order too, so I wasn't sure if you.
that's okay. These are nicely labeled, so I can tell what's what. Let's get
Okay.
people through the exponential derivatives, and then we'll come back and show the other rules.
Okay.
All right. Here we go.
The definition of E
Wait, we just explained before how we got to the E with that. Okay, yeah. So we're gonna have E is the number such that our limit as h equals approaching 0, E of h minus 1 over h will get us 1, and that's just based on the stuff we talked about earlier with our, and it's just still again using the function f of x is equal to b of x, and our f prime of 0 is equal to, what was it, like b of h minus 1 over h. So what this is saying is that the number that'll get us to 1 as h is approaching 0 will be e.
Yeah.
Because, and we know that because earlier
On the dinner tonight.
we were looking at what b of 2 would be and b of 3 would be, and we got 0.69, or yeah, b of 2, b of 3, and we got 0.69 for 1 and 1.1. So we knew that there had to be a number between there that would get us to 1, and we determined that to be, or we just call that number e. So that's
All right. So a few things running in the background here. The definition of the number e that's given in our book is the one that Natasha is showing here. It's the unique number such that the limit as h goes to 0 of e to the h minus 1 all over h is equal to 1. This is a definition that our textbook author chooses to save some time later, and it's not the same as the definition that you may have seen in pre-calculus. But it does turn out to define the same number e, the 2.71828, blah, blah, blah. The things she has on the right side of the board there are statements that will be relevant in a minute. So let me, if f of x is b to the x, then, and I'm sure she'll write this in just a second, f primed is the limit h goes to 0, you know, f prime of x, f of x plus h minus f of x all over h, which is the limit as h goes to 0 of b to the x plus h minus b to the x all over h. Now b to the x plus h is b to the x times b to the h. And then we can factor this b to the x out. And what's left is b to the h minus 1 over h. All right, you remember the tops and bottoms of the fractions are always thought of as being in parentheses. The textbook author claims that this piece is always going to be f primed of 0 because it doesn't have any dependence on x. It's not a necessary thing, but that's what's written here, right? Is that f primed of 0 is the b to the h minus 1 over h. We should have a limit out there, but that's okay.
why we're going to use e. Okay, so okay. So what this means is it means that of all possible exponential functions, where y is b of x, so when y is b of x, the function f of x will be equal to bx. This is the one exponential function example where the tangent line, so whose tangent line will, or they have a tangent line at 0, 1. It has the slope of
that's the problem.
The graph to visualize that better, so better visual. So like we'll just call this like 1, right? So pretty much what we're saying is it comes through. So for f of x to e of x. So we have the tangent line, the slope. Okay, like so the slope right here, exactly like at 1. Which is what we were stating up here, since we know that the limit, the whole thing is pretty much just f prime of x, and again slope is our derivative. So it's pretty much just showing like the whole idea between what this is saying and how we got that, because we know slope's 1 right here. That's why we can say e is 1 as h is approaching, as the limit of h is approaching 0. So okay, and it's gonna lead into like important stuff with the derivative.
Yeah, so what the textbook author is doing here, he's kind of going through a bunch of things ahead of time to justify the thing that everybody in calculus loves, that the derivative of e to the x is e to the x. So he's kind of trying to set up some preliminaries. So when we write down the formula, just using the limit definition of the derivative, we're able to say, oh, see, this piece is 1. And that means that this is going to be, you know, the derivative of e to the x will just be e to the x itself. Because if you just charge through, if you just do like I've done here, you have to handle this limit very carefully, right? This piece is not easy. And what he says, what Stewart, our textbook author, says, is in the special case where b is the number e, so we're looking at the derivative of e to the x, we'll have e to the x times the limit as h goes to 0 of e to the h minus 1 over h. So if this piece comes out to 1, then the derivative would just be e to the x. And that's what he's trying to set us up for here.
Of e of x. So if b, let's just say b is equal to e, so again for b, like we had before up here. So if this is equal to e, then we know that f prime of 0 is 1, and this is going to be an important formula coming up, because it's going to give us a rule for the derivative of natural exponential functions. So this is an important formula. So all this kind of explains how we get the derivative of natural exponential functions and like the rule that goes with it.
All right. So let's move to our next video. 1, 2.
All right, so now we're just gonna show some like numerical evidence for the existence of f of prime at 0, just to show like that there is a number there as the limit approaches 0. Let's look for some numerical evidence. Or f prime of 0, and this is with our equation. And again, just to reference, we're using the f of x is equal to b of x equation, our exponential equation. So what we'll do for this, because we said earlier that f prime of x is equal to the limit as h approaches 0 of b h minus 1 over h, is that we're going to plug in some values both that are greater than 0. We're going to plug in values showing h getting closer and closer to 0, and what we get. And we'll also have some like case numbers for b. So for our first case number, we'll have where b is equal to 2. So we have b, so 1b is equal to 2 in this example. So let me just, you know, this is going to 0, so I'm just gonna say, for what is this one to 0, we'll get the limit 2h minus 1 over h. And you know, you would make values for h, but right now, I'm just gonna show that when you approximate, you're gonna get 0.69, pretty much. And then you'll have when b is equal to 3. Again, we're just looking at as x, or as f prime is 0, it's getting closer and closer to 0, what are we getting? You don't, let me see, so this is gonna be 3. And then you get 1.102.
I cannot understand the f prime of 0. That the 0, it means x is equal to 0 or means b is equal to 0.
Means x is equal to 0. So let me, right, this would be the limit as h goes to 0, f of 0 plus h minus f of 0 over h. So when mathematics is written in textbooks, it's written very terse, right? They skip a lot of steps, and that's our job to fill those in. So if we do that here, remember the function f of x is b to the x. So this would be b to the 0 plus h minus b to the 0 over h, which is what we claim it is. Limit h to 0, b to the h minus b to the 0 is 1 over h. So this piece that we get when we try to cook up the derivative of b to the x in general really is f primed of 0. And then what Natasha's doing.
Wait,
Sorry,
I'm really not following. What's going on?
So let's back up a little
How
bit.
does that equal f prime of 0? I'm not. That's the bit I just. When it jumps to f prime of 0, I'm really not following.
The b to the h minus 1 over h then has some x in it.
Yeah, so
Right.
this does not have any x's in it. This does, but this does not. So just b's and h's. If we set up the limit for the derivative of this function, this is that limit just by definition, and then we plug in this term right here, we can split up using rules for exponents, right? A to the b plus c is always a to the b times a to the c. That's the algebra rule. So this piece I can split up like this. That allows me to then factor b to the x out. And because b to the x doesn't have any h's in it, I can actually pop the b to the x out, and we get b to the x times the limit as h goes to 0 of b to the h minus 1 over h. And the idea here is that you can recognize this limit, this piece, as f primed of 0. So if you think about a handful of different exponential functions, e to the x in particular. Let me resketch this so it's not tilted.
How did you know that that pieces is f prime to 0 of g0?
So I know that this piece, more specifically this piece, right, is f primed of 0. Because if I were to imagine completely separate from this, I just compute f primed of 0. By definition, it's f of 0 plus h minus f of 0 all over h with the limit as h goes to 0. Right? Imagine just this on its own. This is something that everybody could write down. Just for any function, f prime of 0 is the limit as h goes to 0, f of 0 plus h minus f of 0. And then when you plug in for your function, it turns out to be lim h to 0, b to the h minus 1 over h. So this piece that we ran into as we calculate f prime of x happens to be f prime of 0. So the conclusion here is that f prime of x is going to be b to the x times f prime of 0. In other words, the derivative of b to the x is proportional to b to the x. And that's kind of a big step usually in this proof, is justifying that the derivative is equal to the original function times some constant. And that constant happens to be f prime of 0. And then if you zoom in really closely on the graph of e to the x and think about the tangent line, that tangent line appears to have slope 1. So it looks like the slope of the tangent line there should be 1. And that's where the author's definition of the number e is coming from. They say e is the unique number that you can plug in here for b and get 1 out of that limit. Now, what she's doing right now is going through some numerical evidence for different cases here, where b is equal to 2, where b is equal to 3. In other words, you're just going to take this guy, plug in 2 for b, and then some very small numbers for h, like 0.01. And when you do that, you'll get out numbers that are close to, let's see, where do we see it there? So can't quite see on, get something very close to 0.69. And if you do the same thing when b is equal to 3, you get something very close to 1.1. What it's going to turn out to be the case, I think if I show you a little bit ahead of time here. So the derivative, if f of x is equal to b to the x, then f prime of x is the limit h to 0, b to the x plus h minus b to the x all over h, which through some algebra steps we can show is equal to b to the x times the limit as h goes to 0, b to the h minus 1 over h. This piece right here, it is f prime of 0. Right? That's what you would get if you just calculated f prime of 0 using the limit definition. Plugging in a 0 for x here and here, you just get b to the h minus 1. Turns out that the limit as h goes to 0 of b to the h minus 1 over h is the natural log of b. And that's those numbers. That 0.69 that we're getting with b equal to 2, that's like the natural log of 2. The 1.1 that we're getting when b is equal to 3, that's the natural log of 3. So f primed of 0 here is going to come out to the natural log of b. And when b is equal to e, we get f primed of 0 is the natural log of e, which is 1.
1.
So f primed of x in general would be e to the x times f primed of 0, which is e to the x times the natural log of e, which is e to the x times 1, or just e to the x. So that's kind of the big showstopper here, is that e to the x is its own derivative. But the
I cannot follow up. How do you get b to h limiting h approach 0, b to h minus 1 over h is logarithm b?
So that's the piece that she's explaining here. And it's just justified with numerical evidence. Let's let her finish this section and then we'll see if those questions persist.
So you see from, so you know pretty much what this is showing is that there's some number in between 2 and 3 where our f of x or f prime of 0 will be equal to, really, I guess 0. Okay, so let me just make sure I'm saying this right. So what we're saying is there is a number between 2 and 3, yeah, okay, for which f prime of 0 will be equal to 1, okay. And that's how we get this, we'll connect to this, because that's how we usually, this is usually just shown as the letter E.
So the argument here is this. F prime of 0, when you're using 2 to the x for your function, b is 2, that portion of the limit here, lim h to 0, 2 to the h minus 1 over h, comes out to 0.69, which is a little smaller than 1. And when we use b equals 3 for our base, the derivative of 3 to the x evaluated at 0, which is this limit, comes out to something a little bigger than 1. These are calculated numerically by plugging in numbers close to 0 for h. Since when b is smaller, when b is 2, we're getting 0.69, and when b is 3, we're getting 1.1, it's a reasonable guess that between 2 and 3, between those different values for b, there is a number that will make this limit come out to 1 itself. And it turns out to be the case that the number which does that is the number e. Now, I can show you the connection between the textbook definition of the number e and our definition of the number e. It's believed, Sarah, that the first time somebody started working with that was in the context of compound interest. So if you set up the compound interest formula and let the number of compoundings, n, get larger and larger and larger and larger, you start to get this asymptotic behavior to the function. And that turns out to be the number e. So the normal definition of the number e is the limit as n goes to infinity of 1 plus 1 over n all to the n, which is the sort of like the compound interest thing, right? Normally with compound interest, you have a p here, you have a rate here, and you have something else out here. But if you set all those other parameters equal to 1 and then study this as a function of n, this is what we get. And this is approximately 2.7182a blah, blah, blah. This is the normal definition. The textbook definition says e is the unique number such that the limit as h goes to 0 of e to the h minus 1 over h is equal to 1. And I mentioned a second ago that in general, this limit would come out to the natural log of this base. Yiping asked, how would we prove that? That's not an obvious thing at all. And in fact, it's something I'm stating with future knowledge. So if we want to go through this in a way that is not at all circular, then what we need to do is show that this definition is equivalent to this definition. Sarah, sort of. It's the rate of growth for something that is where you're doing a regular interest calculation at every single second in time. So if I borrowed $10 from you at an interest rate of 5%, you could calculate how much interest I owe you once a week or how much interest I owe you once a year. If you calculate how much interest I owe you at every single second in time, then you'll find that the actual interest calculation there turns out to be e to the x, where x is the amount of time that has gone by. And that's where this definition comes from. So to show that these are equivalent, what we do is we take this definition and let n be 1 over h, or h be 1 over n, I guess I should say. Let h be 1 over n. Then, as h goes to 0, n has to go to infinity, right? The only way for this to go to 0 is if this is getting big. So the limit as h goes to 0 of e to the h minus 1 over h would be the same as the limit as n goes to infinity of e to the 1 over n divided minus 1 divided by 1 over n. And we can work with this and turn it into this. That's the idea. So this is all supposed to be equal to 1, remember, right? Their definition is that this thing is equal to 1. So I say 1 is equal to this. Lim n to infinity, e to the 1 over n minus 1 divided by 1 over n. And then I'm going to rearrange this as lim n to infinity. I'll multiply both sides by 1 over n equals lim n to infinity e to the 1 over n minus 1. And then we're gonna juggle some symbols around here. I'll add 1 to both sides, lim n to infinity, 1 over n plus 1 equals lim n to infinity e to the 1 over n. And then I raise both sides to the nth power. Then n to infinity, 1 over n plus 1 all to the n is equal to, over here, I'd have just now lim n to infinity of e. But e is a constant. The limit of a constant is that constant. So lim n to infinity, 1 over n plus 1 is the same as 1 plus 1 over n, so the n is equal to e, is logically equivalent to saying that this limit is equal to 1. So the textbook definition, which is this weird one, is the same as the definition you met in your pre-calculus class. If you accept that this limit is 1, then it's an immediate consequence that the derivative of e to the x is e to the x. Yeah, I do think we may have run out of time here a little bit. So where are we at? 12:16, yeah. So I am going to have to go ahead and stop us here for the day. Let me give you the critical facts here before we go. So results from this section. If f of x is equal to e to the x, then f prime of x is also e to the x. Other results we didn't get to here. If you want to take the derivative of a sum of two functions or a difference of two functions, you take the derivative of each and then add them or subtract them. Derivatives split up nicely over addition and subtraction. Also, the derivative of a constant is equal to 0. These two rules, together with this guy, so a constant multiple, you can always pop out. These three will let you take the derivative of any polynomial together with the power rule. And then if you also know that the derivative of e to the x is e to the x, you can take a derivative of any combination of polynomials and exponentials. The more general case, where I give you the derivative of b to the x, is going to have to wait until we have something called the chain rule. It's not an immediate consequence of any theorems proved in this section. Yeah, I do apologize that we've run out of time here for today, but these are the remaining bits that we need from Natasha's videos. And I want to commend Natasha and Radha for taking the time to put these together. The proof that's given there for the derivative of the natural exponential function, I acknowledge is not a straightforward proof. It's a little bit weird. So in next class, I will run through a proof of this kind of quickly. And we can work some more examples that make use of these things. But unfortunately, we got to get moving. So I'm going to go ahead and end the lecture for today. The last paper, let me see. That was this guy. So what we want to do is here is show that the original definition that we all know is equivalent to the textbook definition. And here's the argument which does that. Alrighty. Okay, guys, I got to end the meeting here. If you need this, take a screen cap. I'm going to go ahead and turn off the share in about 5 seconds. And we will look at some more examples and how to use this stuff next time on Friday. All right, take care, guys.